So today we will start a new concept, chapter, all strings attached. Basically, it's about network science that exploded in 1998 together with the internet. Okay, so I want to start with a very simple example. Have you heard of Collatz conjecture? Anyone? 3n plus 1 problem? Yes, okay. Let me tell you what it is. Just pick a number. Let's pick a number, 10. Is that okay? If it's even, then you divide it by 2. Okay? If it's odd, then you do 3x plus 1 over 2. Do you know this? Yes, exactly. So if you repeat this, so let's do it for 10. 10 goes to 5. 5 goes to 8, right? Because it's 3m plus 1 over 2 is 8. 8 goes to 4, 4 goes to 1, 1 goes to 2 again. Okay? Do you have any questions so far? 16. Actually, I'm a little bit different. So when it's odd, I'm not just taking 3m plus 1, I'm also dividing it by 2 because it's already even, right? So then you can, first of all, Collatz conjecture, conjects, or whatever the verb is, it says that no matter where you start, you will end up at this 1-2 loop, okay? But it hasn't been proved, okay? It hasn't been proved, and I will show you some comments on this. But just let's draw a graph of this, okay? In Mathematica, you have very nice tools to plot graphs. Just three lines, and you will get this one. So this is plotting all graphs between 1 and 30. Okay. What if you go to 10,000? Something like this happens. Okay. This is the plot of the 10,000 Collatz conjecture. So let me just quickly show you some comments. Mathematics may not be ready for such problems. Erdös. And we will come to Erdös in a moment. Actually, right now. Do you know Erdös? Anyone? You haven't heard of Erdös? I'm really happy. So, this is the guy. And he basically lived to produce. Let me just increase. Erdös published around 1,500 mathematical papers during his lifetime, a figure that remains unsurpassed. And if you go to this reference, you will see that using the Mathematical Reviews database, the next highest article count is roughly 823. And he didn't do it alone. He used to travel, meet people. He believed it's a social activity. And it people defined actually Erdös number. Have you heard of it? Well, you haven't heard of Erdös, right? Sorry. But Erdös number is 0 for Erdös himself. Okay? I hope I'm pronouncing his surname correctly. It's 1 if you have an article with him. It's 2 if you have an article with the guy who has Erdös number 1. Does it make sense? So you can actually go to Erdös number, and it's a really big deal. So like there are lists. Where is, there it is. So 0 is Paul himself, and then 1 is, I mean, for example, today I saw someone, Stanislav Ulam was here, so he published a paper with him. And then there is number 2, and 3, etc. Okay. So let's look at his papers. And his most cited paper is on the random graphs with Renyi. So what they did here, let me try to explain. So again, today it's all about networks. Okay. So they took n sites. Okay, n sites, and you can have several connections with them, right? They defined a probability. So what is the total number of possible connections here? Probably something like this, right? So what if there is some probability? So this is the total number of connections. Let's say you add connections with a certain probability. Then what happens to the graph? So for example, this one is a graph that has very low p, because it could have been all connected to everyone, but it's very low. And what you see here is that the graph is disconnected. Do you see? There are these regions. Everyone sees this? They realize that there is actually a sharp transition when you increase p. There is a sharp transition when suddenly the graph becomes fully connected. Okay? And if you allow me, I want to show it with a code. They actually show that they show several things. One of the things, let me show you the paper. Are you with me? This is the paper dedicated to someone's 50th birthday. So you can see that it's purely mathematical, like theorem, proof, etc. Just so that you can say that I have seen that paper. They realize that that probability is around ln n over n. Just check out the paper to see why.
What probability was?
Probability is the probability of connecting to, like you choose two sites, and with this probability p, they connect. And when it's above ln n over n, the probability, suddenly the graph becomes fully connected. Below, suddenly it's disconnected. Okay. Do you want to see the code? Yes, you do. So let me see if I can explain this code. So this is the number of sites. Okay. M is number of probability points. Like we will scan the probability from 0 to 2 times ln n over n. You can see it here. We will have a line space. Do you know what this with this line does?
Linear
Yes, between 0 and 2, and there will be m points, right? So probability will change between 0 and 2 times ln n over n. Then we start for each probability. So for example here random n by n by n random numbers. Okay, and then let's start this one. Start adjacency. I hope I wrote it correctly. Doesn't seem correct. Let's check. Adjacency. It's correct. Adjacency matrix with zeros. Can someone tell me what this adjacency matrix is? Just guess. If you don't want to guess, then let me tell you what it is. So let's say these are nodes. So 1, 5, 2, 3. Let's also. So adjacency matrix for this one is right now 0. But if I add this, okay, then I will add 1 to 1, 5 and 5, 1. The rest will be 0. So adjacency matrix actually is the number is 1 if you have connection there. It's 0 if you don't have connection there. Okay? Well, I haven't told it yet. So then, do you see this line? With half of the probability, so I have random numbers, n by n random numbers. If a certain site is smaller than the probability, right? So if the probability increases, there are more possibilities of putting a vertex there, right? Add connections with probability p. So you can see that afterwards I will actually symmetrize. I actually symmetrize the matrix. Do you see that? Yes.
Wasn't there to be a connection? Isn't it like R is greater than probability?
No, it's smaller because let's say probability is 0.1. Then R being smaller than 0.1 is 10%. Do you agree? Are you perfectly convinced? Then ask again. So R is any number between 0 and 1. And I want it to be, for example,
so we are comparing the probability with R. What is R?
R is random number
Random number, but
between 0 and 1.
okay, but what?
Let's say it's 0 to 25. Okay. Then it's big. It's actually not smaller than 0.1. Let's say probability 0. Then you will not have 1 there. You will not have connection there.
I understand this mathematically, but I don't understand why we compare it to probability. It's not random.
Okay, let me tell you. So random number 1, 10. It will give you, no, let's do it this way.
I understand it called like an.
So these are random numbers.
Okay.
And let me say answer 0.1.
Okay, it's going to give you some language. Okay.
Yes. Tell me.
No, so I think the
The question.
why are we rolling the dice for every node and then comparing that with this
Yes.
probability?
Why is it like benchmark?
Yeah. Why is it random numbers in the first place? What is the connection?
why are we generating random numbers for this?
Because we add vertices with a certain probability.
Okay.
So it's kind of like Monte Carlo, we're just rolling the dice and trying to see how many of them establish the connection and how many
Yes.
could. It's like a trial. We're just doing a random trial. Like that.
I know you are not convinced, but maybe we can discuss later. So why probability over 2? Because I'm going to symmetrize it. So it's I have to do it probability over 2. So symmetrize the matrix. Symmetrize the adjacency matrix. Okay. Then I remove diagonal elements so that the node is not connected to itself. Remove diagonal elements. Did you follow so far? Yes. Then there is this miraculous lines of code that I don't understand, that I found from someone. I should have mentioned his or her name, but sorry. So what this super awesome function does is it takes you from adjacency matrix to the connectivity, like how many graphs there are, what belongs to whom, etc. Yes, like so C will be okay. I need to show you an example. Maybe do I have an example here? Codes. Yes, this is a nice example. So what is the probability here? Let's make it over 2. So I want to show you C. So C has 989 cells, and if you look inside those cells, so for example C1, let's increase this one to times 0.9. Just let me find a nice number. Maybe this is fine. Anyways, inside these cells, you will have the nodes that are connected. Okay, so I define connectivity as the size of C, which means that the total number, 1 over total number of clusters. So what do you expect according to Erdős? Did you follow so far? So for example, what is the number of clusters in this graph? How many clusters are there? 2, 3, 4, 5. Yes, you count also the totally disconnected nodes. So when you have a fully connected graph, then it is 1, just 1, okay? So 1 over 1 will give you 1. Otherwise 1 over 5, etc. So let me run this and see whether it gives you a nice answer or not. So do you see these points? No? I should increase this marker size. There might be some outliers here, so the graph didn't get fully connected, but there are 2 parts. But you can see that after this log n over n, or ln n over n, suddenly the graph becomes fully connected. And it's a random process it's interesting that it suddenly gets disconnected. So this might be the first very, very important result in graph theory, okay, or in network science. Let me talk about other stuff. By the way, I think 10 years ago, I wanted, don't judge me, okay? I wanted to see, actually I wanted to see this one, but let me. Do you know the puzzles like this? Like there is this thing that is empty and you can move these things. Do you remember? So I wanted to see the network behind it. Well, I couldn't do it with this big thing, but let's do it with this one. 1, 2, 3, 4, 5. And then there is this emptiness. So basically, excuse me, it could go to this state, right? Like this, or anywhere else. Let me show you its. Are you ready? This is the eye candy of today. So this is what I got. Do you see it? Each one represents a state of the game. Do you like it? Do you understand what I just showed you? Yes? Good.
Is it just too much number of states or just like 6?
Let's see. Let's see. Just let's assume that each one can be. Gerçi it's not, right? So like 2 times, 3 times, 4 times, 5 times, 6 times. No.
Yeah.
This gives you 720, and for the reasons of some symmetries and some restrictions, it's actually divided by 2. So it's 360 nodes. Fun. It's not a buckyball. It's a different kind of beast. You might wonder how I found this geometry. By the way, you can see that there are nodes that go to 3 places and nodes that go to 2 places. Can you tell me what they are? Exactly. So do you see why you are so good? So, okay, very good. How I reached this one, I just took the first nearest neighbor, second nearest neighbor, third, fourth, and I connected them with springs of that size. So if you let them jiggle, they will end up on a surface. That was fun. But let me talk about other important discoveries in network science. So do you remember I was going to talk to you about Strogat's, this main article. Do you remember this? Small World? So let's look at that article. And literature. So I will show you 3 more articles, okay? One of them is a Nature paper, Small World. Collective Dynamics of Small World Networks. So basically what they do is they start with a regular network where everyone is connected to its neighbor and maybe next neighbor, right? Then they define some P, which is randomly they connect one to the other. Have you heard of the concept 6 degrees of separation? Anyone? No? So 6 degrees of separation is a popular network theme where people say that in real world, anyone is only 6 degrees of separated from the other one. So if I know Tamer, he knows Ahmed. If I don't know Ahmed, my degrees of separation with Ahmed is only 2. Does it make sense? So my degrees of separation with Obama, let's say, is less than or equal to 6. This is a popular concept.
So someone you know who knows
Yes.
all
Yes. Yes. Only 6, maximum 6. And that's the concept of small world. You know, like you bump into someone and you say, it's a small world. Do you understand my point? Yes, tell me.
Do we count, like, for example,
Yes, we do.
rector knows
Definitely. Exactly. Exactly. That's okay. That's a very, very good point. So there are these important nodes. That's exactly these nodes that connect very distant points. Do you understand my point? So that's why degrees of separation suddenly decreases. So it becomes a small world. And they saw that just similar to Erdős's paper, but also very, very different from that. They saw that when you increase this P, like going from regular to random network, and in between you have small world, you suddenly decrease the degrees of separation. And for example, they did a lot of work with it. One of them is here. I wanted to show you this. We have also examined the effect of small world connectivity on 3 other dynamical systems. By the way, the one that they looked at was this disease spreading. So small world makes disease spreading way faster. That's one thing. Another thing is for cellular automata charged with the computational task of this I don't understand, but let's see this one. For the iterated, this comes for you, Jam. For the iterated multiplayer prisoner's dilemma played on a graph, we find that as the fraction of shortcuts increases, cooperation is less likely to emerge in a population of players using a generalized tit-for-tat strategy. You see? So what do you think is this article 26?
So that one.
Yes,
I don't remember.
the evolution of cooperation. Do you see? So at least I have some connection with the last lecture.
Yeah, I don't think it's appropriate to ask this one, but with the strategy with nodes and other individuals is very different, right? Because if you're a node, you have some people behind you.
Yes.
But if you're an individual, for example, it doesn't like how you can see. If you're an individual in that node, it makes sense to cooperate with the people in the same node, but not with the other nodes, things like that. So I don't understand like how.
I don't understand either, but let's think about it, and I promise I will come back to you with that. But I have a couple more surprises, so thanks for that question, though. So this is a nice paper, right? 36,000. Then there is, what is the time? 1998. Then there is this one, 1999. Emergence of scaling in random networks. Do you see that the network science itself had a transition that is very similar to network transitions? And this guy himself is an example of networking. Do you see? Like error and attack tolerance of complex network biology. He's a physicist. Understanding individual human mobility patterns. and evolution of the social network of scientific collaborations, network medicine, the origins of bursts and heavy tails in human dynamics, etc. So if you want to change the subject for some reason right now, this is a good subject. So let's see their paper. Did you see that Small World paper had a very simple idea? Do you see that? Another very simple idea. This here they ask why the networks have the scale-free properties, why they are fractal-like. Okay, so if you plot logs in log scale, let me show you the plot. So these are the websites, let's say, that have k links pointing at them. Okay, and this is the number of those websites. So if you plot it in the log scale, so there are very few websites that have billions of links. Billions too much? Do you understand the message, right? So let's say there is one website with billion, then there are 10 websites with 100 million, 100 websites with 10 million, etc. Do you understand my point? But why is it so? So they discovered a very simple mechanism that would end up in this architecture. Let's read the abstract. Systems as diverse as genetic networks of the World Wide Web are best described as networks with complex topology. A common property of many large networks is that the vertex connectivities follow a scale-free power law distribution that I just mentioned. This feature was found to be a consequence of two generic mechanisms. One, networks expand continuously by the addition of new vertices. Do you see how much pain they had to have to go from a physicist view of starting with n nodes to a biologist view of starting with single node and adding new nodes? Do you understand my point? So suddenly looking at it naturally gives you new insights. And then new vertices attach preferentially to sites that are already well connected. This is called preferential attachment. So if you already have many links, then it's more probable for you to get even more links. Money makes money. Okay? It's also called Matthew effect, which is from Bible actually. Are you with me? Then they check, for example, if we don't actually grow the network, but if it starts from somewhere, it doesn't go to scale free, or if you don't use preferential attachment. So these two things, growing and preferential attachment, are necessary and sufficient mechanisms to get a scale free network. Okay? Are you following? They even give a model, a very simple model, which says that the slope should be 3, but there are other slopes too. So, for example, actors, collaboration, connectivity, World Wide Web, etc. This is, I believe, power grids. So this paper explains why you have hubs. Okay? Do you have any questions so far? Yes. And the last but not least is another paper from 1998. Do you see how precise the transition is? And who are the authors of this paper? Yes. Yes. Let's actually see them. I see. Okay. It's this paper, I believe. The Pagerank citation. Larry Page, Sergey Brin. Let me first talk about PageRank, what it means. So as a website might have few links than others, but if the link that is coming to it is coming from a website that have lots of links, then that site is also important. Do you see? So for example, this C, compare it with E, it's way important, right? But it's only getting one link, but it's getting it from B, the giant. It's like if you have a link to your paper from a nature paper, then it tells something about the quality of your paper. Do you understand my point? So they came up with this algorithm. I won't bother with you with this. So this just take these lines. How much money would you give for these lines?
Back in the time. Too much.
Let me show you something. Okay. Ouch. Yes. Let's see. The name PageRank place of the developer Larry Page, as well as the concept of a web page. The word is a trademark of Google, and the PageRank process has been patented. However, the patent is assigned to Stanford University and not to Google. Google has exclusive license rights on the patent from Stanford University. The university received 1.8 million shares from Google in exchange for use of the patent. The shares were sold in 2005 for $336 million. Okay. What is not simple is not important. Okay. That's the message for today. So it's a simple algorithm worth, by the way, this thing in general, which node is important, is the question of network centrality. Okay, and which node is central? If you want to control Middle East, which country you have to play with? Something like that. Actually, I have a very nice YouTube video with Axelrod explaining the interaction between Turkey, Iran, Syria, and states. And I will send you the link, okay? Tell me.
No, I was just wondering, it's only after they have established these connections can you apply these algorithms?
Yes. Yes.
It doesn't take into account craziness. For example, you have these countries, but let's say some lunatic takes power, and then
Well, you can never be sure that that is really their own craziness or something.
I guess.
But I just gave an example. Okay, let's talk about metabolic networks. Like if you want to kill a disease, if you want to stop an infection, which part you should definitely make a quarantine? Let's say it's like you don't have enough tents or something. Do you understand my point? It's a general concept. Tell me.
Even in politics, even if there is a crazy guy, isn't it like a very stable? We shoot Russians' airplane, and then 2 years later we become allies because our connection makes it very stable. For example, if you want to do something in the Middle East, for example, Iran can't do a lot of stuff in Syria because they are Shia, and we are Sunni Muslim, and they ally us with us. So even if you do something very crazy, because we are the cultural node, they have to make a line to us.
Yes. So Turkey is important. Yes. Yeah. It's okay. It's okay.
So my point was different. My point was like, okay, you have these connections.
Yes.
Let's say, and then in the paper he said new node.
You are saying there should be some randomness.
No.
Is that no?
The
paper said that this process continues without any scaling, scale-independent exponential growth, right?
Okay, that was different paper. This is a different paper.
It doesn't explain this node connection.
Okay, so that paper explained the architecture of the web without looking at the centrality at all. Okay, then once it's growing or during the process, you can apply this algorithm and you can draw them with different colors to see which one is central, which one is not. I mean, the thing, one of the nodes that don't seem important might be actually important.
That's my point. Yeah.
Yes.
So let's say you have this new node coming in.
Yes.
And you have this established
Yes.
network. So according to this,
Yes.
does this algorithm factor in
Okay.
the potential of that new node?
So let me tell you one more thing. There is this thing called bounded rationality, introduced by Herbert Simon. Do you remember him? We looked at his. So maybe a node is actually very important. For example, let's talk about scientific topics. Maybe some of them are really, really important, but you don't follow them because the crowd is not following them. Okay? So it's two different things. This Barabashi paper explains you why there are these mass delusions, or not delusions, but mass followings, right? But this PageRank algorithm brings you the truth inside the. It looks at the whole thing. Because of the architecture of the network, you realize that some nodes doesn't get enough attention, but thanks to that's why Google is so successful, because it doesn't use only PageRank algorithm. There are others, but it brings you the most important ones, the most relevant ones, not the most clicked ones. So it's hard to fool it. It's hard to fool this algorithm. Okay. There are a couple other things that network science introduced, but I feel like you already got bored. But some of them, for example, how do you, for example, when you look at a certain paper A, then you get suggestions like paper B. How do you get those suggestions? Well, maybe these days it's all machine learning, etc. But network science actually brings you another insight. One way is to let's say this paper didn't cite B, but they both cited C. Then they have to be relevant in some sense, right? What if they both also cited some article D? Then they are definitely have something in common. Can you, so this then connects A to B. Can you think of any other way of connecting two papers? Consider network science.
Yeah.
No, like in the previous lecture we saw, for example,
Let me tell you the answer, because it's way simpler than it. Do you see that C and D are also connected here, even if they don't cite each other? So another connection is if two papers are citing U. You understand? So these kind of very simple ideas actually make network science very powerful. So you can find relationship between two things that don't seem related at first sight, but then it connects them. So do you have any questions? What was your question? Or what was your answer?
like in the previous are we connected in, for example, cloth choice and food choice, etc. Keywords is something like that. How much of both of them similar to each other?
Yes.
So from that, after one point, for example, if there is more than 10% match.
Okay. Like, I see. The dissemination of culture kind of thing. Yes. So, feature extraction, right? That's a property of neural networks and deep learning. We can go into that in the next lecture, or we might not. I'm not sure yet. Do you have any other questions?
So is this why we get weird Facebook friend requests? You may know these people as well.
Exactly.
I see these faces, I'm like, I don't know.
Exactly, but
I think it figures out.
But let me tell you, I have no social networks anymore, like not even ResearchGate or LinkedIn. But back in the times when I had LinkedIn, those suggestions were excellent. I mean, I see someone on the street every day. I don't know her. Then she comes out in the suggestions. Then somehow it finds out why the reason why I saw her every day. Thank you all a lot. Take care.